Hello, operating systems people. This is Gabriel Palmer, and today we are going to be talking about security and protection. This is the second time I'm recording this because I forgot to switch things over properly. Great. I didn't mess up this time. All right. So protection and security are all about kind of asking who should have access to what within a system, right? So that what is resources. So a system consists of a collection of resources. These could be the physical resources, memory, disk, network interface cards, that type of stuff. Or it could be, of course, the virtual abstractions that we create as an operating system. Things like processes, files, semaphores, etc., right? So these are the things that we want to protect and ask who should have access to them. And who is accessing those things, that's principals. So principals are the set of all those entities or actors that are trying to access system resources. These could be users, processes, threads, whatever you want to think of them as. And protection is just that idea of ensuring that all resources are only accessed by those principals that are allowed to do so within the system. So when we think about implementing security within systems, we need to have some model for thinking about how accesses are made, and that's usually based around a reference monitor. So we have our principals that are making requests to access different resources in the system, and a reference monitor is an implementation within the system that must be trusted, must work perfectly, and it decides, yes, you can access certain resources, depending on which principal is requesting them, or it can give them a big old bag of nope, right? So it is the thing that decides yes or no whether a request from a principal for a certain resource can proceed. So all resource accesses through the system must go through the reference monitor, or else it's not able to actually define the security of the system, right? Now, of course, the reference monitor itself must be implemented in a good way. And it must be implemented in a way whereby the principals themselves should not be able to corrupt them, right? Okay, so how do we think about a reference monitor? We know that a reference monitor must be trusted, which is to say that we don't have an option, right? We must trust it to do what it is supposed to do. For us to justifiably trust a reference monitor, it means that the reference monitor should be implemented in a way where it's trustworthy, right? And one way to think about this is the economy of mechanism, which is to say that we should focus on simplicity in implementing the reference monitor. If it is as simple as possible, that means it's more trustworthy, right? We have a higher confidence in its correct implementation of kind of however it's supposed to be doing its access control decisions, saying yes or no. It's very important the reference monitor is protected from the principals that it is making decisions for. If a principal could access a reference monitor or influence a reference monitor's decisions in a bad way, then that is in some sense a privilege escalation, right? That principal is getting access to some resources that it otherwise should not potentially have access to. So privilege escalation is something that we try to prevent within systems, and is one of the most common ways in a lot of monolithic systems to, in essence, take over the system. So the big question here is, how does the reference monitor decide if a principal can access a resource? So this is what we need to answer. And some of the guiding principles that intuitively we might think about this might be things like need to know, and if I told you I'd have to kill you. These are great kind of intuitive ways that we know in movies to kind of decide who has access to what types of resources and what the consequences of that are. But they're an intuition. They aren't that great for designing a system around. So one of the key ways that we try to decide who should have access to what resources is through the principle of least privilege, POLP. And the principle of least privilege essentially says that of all of the resources in the system, a principal should have access to the minimal set of those resources to be able to accomplish its goal. So for a goal that requires access to some resources, you should only have access to those resources and not the rest of the resources in the system. You should have the least privilege to all of the resources to be able to conduct your goal, right? I think this makes intuitive sense to the point where people assume that it's kind of the default, but it's not. If you think about it in a system like Linux or just generally a Unix variant, you have access to be able to make any system call within the system, whether your application actually needs to make those invocations or not, right? So the principle of least privilege is really important in deciding kind of who should have access to what. When we start thinking about how to formalize that notion of who has access to what, we start thinking about typically an access control matrix. And the access control matrix is essentially a two-dimensional array where we have all of the resources along the top, all of the principals along the left. So here we're thinking about a system with only users as principals and like files, network, printer as the different resources in the system. And each of the cells at the intersection of the principal and the resource define the operations that principal can perform on that resource. So for instance, user 1 can write to file 2. However, wherever there's a dash within this access control matrix, that principal can perform 0 operations on that resource, right? So this is a kind of, I don't know, pretty intuitive way to think, yeah, okay, I mean, we could think about just having this access matrix, and then a reference monitor just needs to look up in the access matrix to see whether a principal can have access to some resource. Fine. Okay. So access control matrices, they typically are broken into two different, we conceptually think about them in two different ways. The first is the mechanism. How do we actually implement the access control matrix? So literally, how do we write the code to encode that table that we just saw, right? And then separately, we think about the policy, which is to say, how do we decide how the different cells within that access control matrix should be filled out? Who should have access to what resources and should be able to perform which operations on them? And as an aside, the separation of the mechanism and the policy within the system is a kind of tried and true system organizing principle since the early 70s. And we often want to implement mechanisms that are polymorphic to multiple policies. They can implement many different policies. So we might think of that as looking something like this, where we have a number of policies that could be implemented on some core mechanism within the system. So the goal is to make these mechanisms as general as possible so that we can support the largest variety of policies while still having that mechanism, in this case, make sound access control decisions. So, okay, let's talk about the mechanism first. How do we actually want to implement the access control matrix within the system? Of course, the most straightforward way to do this is to just think about actually implementing it as a table, right? Two-dimensional array, great, throw it in memory, you're done. Your reference monitor just looks at the current principal, looks up its entry, looks at the resource that we're trying to access in there, makes a decision, done. Real quick, right? Easy. So do we use this? Is this how reference monitors are implemented? What are the trade-offs in this? Think about all of this for a little bit, pause it, come back. Okay, so if we actually use a global table, it has the huge benefit that it is using the economy of mechanism. It is a very simple implementation, right? So this is a big plus, but unfortunately that plus is completely offset by its negatives in terms of resource utilization. If you think about most systems, the number of principals on the system and the number of resources on the system, the number of principals could be the number of users on a small system, which is not that many, so maybe that's okay. Or it could be all of the students within the School of Engineering and Applied Sciences at GW. Or it could be all of the citizens in the United States, right? This is starting to get really large. Or more realistically, you could think of the principals as being any client that is connecting to some server, right? Now that's absolutely massive, right? That's potentially even much larger than the number of citizens. In the number of resources, we have a comparable problem. There could be a vastly large number of resources on the system. We could think of every page on the system as being a different resource. So this is a lot. So if we take the sum of both of these, the number of principals times the number of resources, that access control matrix is going to take up a lot of memory. You might observe that it's probably relatively sparse, which is to say most resources can be operated on by not many different principals, right? So in that case, you might try to figure out some data structure to use to compress down the resources needed for that, but inevitably it's going to be relatively complex, so we start giving up that economy of mechanism that we once had, right? So the global table is not generally that useful, but thinking of the system in terms of this table can be useful. And we can derive two different mechanisms for implementing essentially this access control matrix style permission checking within a reference monitor. The first of them is access control lists, or ACLs. And an access control list is essentially a column within the access control matrix. So here we see a column for file 3, and we can see that if we store an access control list with file 3, then it will include only user 2 being able to write to that file, right? So every single resource in an ACL has a list of all of the data associated with it, with all of the permissions associated with it, which principal should be able to perform which operations on this resource. So for files, ACLs are a tried and true mechanism within the system. They've been supported in Windows for a very, very long time. They've been supported in Linux for a less long amount of time, and most secure systems provide some version of ACLs, usually for things like files and directories. Not necessarily for like every page within the system, or for non-volatile resources. So now, whenever a principal attempts to perform some operation on a resource, the reference monitor will look up in that resource's access control list to see if that user is allowed to perform that operation. Okay, so this is ACLs, essentially a column within the access control matrix. So that might give you some hint as to what the next mechanism is, which indeed is a capability table, which is effectively a row within the access control matrix. So here we see for user 2, all of the operations it can perform on all of its resources. So user 2 can perform operations on file 1, file 2, file 3, and on the network, but not on the printer. And on the file 3, it can write, but it can't read, it can't execute, etc. So this is effectively a data structure stored with a principal. And because principals often are not themselves stored in some sort of a recognizable abstraction on disk, capability tables are usually for kind of non-volatile resources, whereas ACLs are stored on disk for the volatile resources. So a capability within a capability table is effectively an offset into the table. So here, capability 0 for user 2 gives it access to write to file 1. Capability 1 lets it execute file 2. Capability 2 lets it write to file 3, etc., etc. So we think of the capability table as the sum total of all the operations a principal can perform on which resources, and we think of a capability as essentially an offset into this table. So the access rights for a resource are encoded in the capability table, and the notion that you have a capability, which is to say you have a entry in your capability table, that capability itself denotes the ability to perform operations on some resource, right? So now the reference monitor, when it receives a request to simply write to capability 2, all that it needs to do is check that entry at capability 2 within the capability table and see whether you have write permissions. And indeed you do, and it identifies which resource to be able to provide those on, in this case file 3. Now, of course, for both of these approaches, it's important that neither the capability tables themselves or the access control lists are directly modifiable by the actual principals themselves. Okay, so let's go through an intuitive example. I don't know if both of these companies are still doing their thing, but Bolt Bus and DC to NY were two buses that would run buses from DC, District of Columbia, to New York, which is about a 4-hour trip. And they both handled access control in very different ways. So one of them used a ticket as a proof of entry. So you provide the ticket, and that ticket alone denotes your ability to get onto the bus, right? Doesn't even necessarily need to have the passenger name. So long as you have a ticket, you're good to go. On the other hand, the other company provided a list of passengers. So there was a list that somebody actually needed to check on the list to see whether a passenger was on it before they were allowed access. DC to NY had 2 employees per bus, whereas Bolt Bus had only 1. So, which one of these mechanisms maps to access control lists, which maps to capabilities, and which one of them, DC to NY or Bolt Bus, do you think used which mechanisms? Think about it for a second, pause, come back. So in this case, DC to NY had 2 employees. It had 2 employees, one of them was always checking a list of passengers as a new passenger arrived. This is a relatively expensive operation for them to perform, which maps to access control lists. If the access control list gets relatively long, many different people have access to that resource, it can be relatively expensive to actually check that type of permission. So DC to NY had 2 employees, one to oversee the access control list effectively and one to actually drive. Whereas Bolt Bus took the ticket as a proof of entry. So what they did, they essentially treated the ticket as a capability to be able to access the bus as a resource, right? And of course, they only needed 1 employee per bus to do that because, I mean, how hard is it to take a ticket? Right? Presumably, if somebody falsified a ticket, which you can't do in a computer system as easily, but presumably if somebody did, then they do an expensive operation of validating that everybody had a valid ticket. But I never saw that actually as a necessary thing. Okay, so let's compare the trade-offs between these 2 different mechanisms for providing access control within the system. For the reference monitor to actually implement these 2 different things, ACLs and capabilities, for ACLs, it can be relatively time-consuming to check lists whereby many different principals can access a resource. So ACLs tend to be more heavyweight and more time-consuming, whereas capabilities, a capability itself, essentially an index into a capability table, denotes all of both the resource that you're performing an operation on and which operations can be performed. So it's really just a lookup in a logical array, which is very, very fast. So a reference monitor can typically be faster at providing its key operation of deciding yes or no whether you should be allowed to actually access a resource for capability tables and for access control list. Delegation is the operation within a secure system being able to effectively share a resource. You have access to a resource and you can provide that access to another principal within the system. Ergo, you both share access to that resource. For ACLs, access control lists, it's relatively simple. It's just kind of appending onto the ACL, right? That may be somewhat complicated because it might require memory allocation or disk allocation, whatnot, but it tends to be relatively fast. For capability tables, it's essentially just allocating a new capability into some other principal's capability table and then just kind of essentially providing a pointer to the resource that you are referring to and denoting the operations you can perform. So it's relatively fast in this case as well. So delegation is actually relatively fast in both of these systems. Revocation, however, is where these 2 mechanisms start to be pretty different. So revocation is the idea that we want to remove previously granted rights, and it is actually more complicated than you'd think it is. Because if you delegate some access to a resource to another principal, now they might be able to delegate that resource to other principals as well. So you can kind of think of this as being kind of a tree of delegations within the system. And the question is, for revocation, you typically want to, how do you actually remove all of those delegations? Not just the one to the one principal that you made, but to all of them. So for ACLs, it could be a little complicated because you can very easily remove the principal who you delegated to from the ACL, but somehow you need to track the delegations, how each of the resources in the ACL got access to that, what delegation caused it. So you essentially are going to need to iterate through the ACL to be able to provide this revocation, but that's okay. You're iterating through a single structure that's relatively easy to find, so it's relatively fast. For capability tables, however, it's a little bit more complicated. When you delegate a resource to another principal, you're adding a reference to it, a capability to it, in their capability table. When they delegate it, it does the same for another principal. You essentially need to track all of these delegations as a tree of delegations, so that when you revoke access at a certain point, this principal says, I want to remove that principal's access to this resource, which means also that you want to remove all of the recursive or transitive delegations that were made. You essentially need to go through this entire subtree and remove all of those capabilities from the corresponding capability tables. So you need to track all of these capabilities, you need to track all of the delegations, and they can be distributed across all of the capability tables in the system. This can be relatively complicated. So for revocation, ACLs do it much more gracefully than capabilities do. Auditing is a really important thing within secure systems, and it's the idea that you want to be able to look at all of the resources that a principal can access. And typically you want to ensure, you do that audit, you see all those resources, and then you want to essentially see whether they should have access to all of those resources or not. So for ACLs, you kind of need to iterate through every single resource in the system to see which principal that is associated, that if the principal in question that you're auditing is within each of the resources ACLs. For capabilities, it's simply iterating through a capability table, right? So for revocation, for capabilities, you might need to iterate through all of the capability tables. For auditing, you might need to iterate through all of the resources for ACLs. So you can see there's kind of this weird mirroring here, that revocation is a little bit harder in capability tables, auditing is harder in ACLs. So these are... There's no slam dunk here, right? Both of these mechanisms make trade-offs. They're actually often used at the same time in the same system. They are often complementary, not competing mechanisms. So a not perfect example that I'd like to use here is a drink bracelet at concerts. So when you go into a bar or when you go into a concert, often they will check your ID at the door one time. And that's, I'm saying that this is kind of like an access control list type check because you're having to kind of iterate through your wallet, right? To find out, okay, do you actually have an ID that denotes your age at the proper level, right? But then once they actually check that kind of access control list equivalent, which is not a perfect analogy, I apologize, they give you a bracelet. Simply having that bracelet, that capability, denotes your ability to access the resource of the booze, right? So once you have the bracelet, there's cheap verification of your age as if it was essentially a capability table, just looking up a single entry in it, right? An index into it, which is fast. So, why do they do this? They do this because they don't want the bartenders to have to spend all of their time checking people's age, right? That's a very expensive thing to do. You're going to need to hire more bartenders. So instead, they front load the cost of that verification to when you're entering into the concert when time is less valuable. And that's when you do an access control list type check, right? Now in real systems, we see this type of thing as well. We talked about the polymorphic file descriptor interface, the virtual file system API within Unix. And we talked about the open API performing an expensive check on file system resources denoted by some path, right? And it returned a file descriptor. So what is often done during open is an expensive operation. It's assessing whether you have permission at each level and checking access control lists at each level, right? But then once that's done and you know that you do have access to some file or directory, from that point on, you have a file descriptor that can be used to read or write directly to that file or directory without needing to go through that expensive check again. So looking at the picture that we've seen multiple times before, we typically store the ACLs within the inodes for the system associated with each of the directories and files. And once we do open one of those resources denoted by the inode, and we've ascertained that in the ACL we have permission to it, then we simply add this file structure that directly points to the resource and add it into our capability table, i.e. our file descriptor table, right? Having the file descriptor alone denotes our ability to access that file or directory. So you can see that these are not always competing mechanisms, but instead systems are designed to try to use kind of the benefits of each of them. So this is all of the mechanisms within the system and how I want to kind of discuss the mechanisms within the system. For providing an access control matrix and how we might implement them in a reference monitor. Now I want to kind of look at the other side of that, which is the policies for deciding who should have what access to which resources in the system. And a famous policy for this is called Bell-LaPadula, and it kind of looks at the system in terms of information flow. Information flow is essentially the idea where we are looking at all of the data within the system encapsulated in the resources, and we're trying to ask if all of the permissions within the system were exercised, that data could flow from file to file and principal to principal. And as it flows throughout the system, we want to track that information flow and we want to constrain it in some way. So an example of this information flow in, again, kind of real world is, assume that I'm an idiot and I have my password written on my desk. Okay, fine. Trust me, that's not how it is, but let's make that assumption. Let's also assume an incorrect assumption that the TA has a key to my office. Okay, so the TA has a key to my office, they can access everything in it. And the department administrator has access to the TA's desk, but not my office. Okay, if we look at the information flow of the system, we see that my password is on my desk. The TA has a key to my office. My office encapsulates my desk, so therefore my desk with my password can be accessed by the TA. The information of my password can flow to the TA, the principal TA. The TA has access to their own desk, so that information could pass to any of the documents on their desk, for instance, if they wrote it down. The department administrator has access to their desk, therefore the information on my password could flow to the department administrator. Again, we're just looking at all of the accesses that are allowed within the system and trying to say, could the information flow from this principal to that principal, right? And we look at all of this information flow and ask ourselves, should, after all that information flows throughout the system, should all the principals who have access to all of this information really have access to it, right? And the Bell-LaPadula policy tries to constrict the information flow by design and completely prohibit different forms of information flow in the system. So if I don't want my password to eventually be able to flow to the department administrator, probably a safe assumption, hopefully I could design a policy like Bell-LaPadula that would completely prevent that from happening. Okay. So Bell-LaPadula is based on the idea that we classify all of the resources and principles into levels. This kind of maps well onto kind of MILS, or multi-level information security, which is kind of the military classification for, secret, top secret, etc. I'm just going to call those classification levels here. And the big question is, once we separate principles and resources into different levels, into different classification levels, how should we define rules for how reads and writes should be allowed to be performed between those different levels? And this is what Bell-LaPadula essentially specifies. So Bell-LaPadula is based on two simple rules. Once we classify all of our users and resources, X, into different classification levels specified by C of X, then we can simply say that we have the simple security policy and the star property. You should read through these, internalize them. In all of my previous experience with people, reading these out verbally does not lead to anything useful. So please pause here, read through these, try to internalize them, pause, I'll wait for a sec. Okay, all that these are saying is that you should be able to read downwards. So you should be able to read resources at the same confidentiality level as you, and those that are lower than you. So the president should be able to read the news, right? The news is not as confidential as the information that the president has, but the president should be allowed to read the news. You should be able to read downwards, and you should be able to write upwards. So any citizen should be allowed to write a note to the president and share their grievances with them, right? So you should be allowed to write at your own confidentiality level and upwards, so that information can flow upwards, but information cannot flow downwards, right? Okay, so an example of this in this class, right? So I'm at the top level. I'm at the top level essentially because I can assign grades, right? That usually is what it all boils down to. I have the ability to write out the grade assignments to the overall university systems, right? I also have the ability to read the class feedback, to read grade questions, whatnot. Below me is a level with the grader in it. The grader has access to the grade sheet, which they can read and write to. I can read from it. I don't typically write to it, right? So my information cannot flow down into that grade sheet. It only flows upwards. They have access to the submissions, the homework submissions, to the auto grading, all of that stuff. So they can read the submissions. I can read the submissions, but we don't typically write to it. I could not write to it. The grader could, and I guess they do when they actually wish to publish your grades, right? We have the TAs and undergraduate TAs. They have access to the class list, but they do not have access to submissions. They do not have access to the auto grading infrastructure or the grade sheet, right? I like to try to keep that information from them. And all of you, the aspiring operating system hackers, have access to all of the lectures, labs, and homeworks. Of course, so do I, so does the grader, so do the TAs. We can all read this information just fine, right? All of you, students within the class, can write submissions, right? So you can write upwards, but you can't necessarily read the class list. You can't necessarily read the auto-grading infrastructure. So this class does not implement Bell-LaPadula, but you can see that a lot of there are good analogies here between how the class manages a lot of its information flow from all of you upwards, but then very carefully mediates how information flows downwards to all of you, right? I'm very careful not to provide other students' grades to different students, right? That's a big no-no, and that's why information flows upwards but not down. Okay. So we've talked about the mechanism and the policy behind how to implement an access control mechanism, an access control matrix, basically. But the last thing that I want to talk about is effectively how we think about really implementing these systems. And I'm not going to go into this in much detail. Please feel free to ask more questions about any of it. So the big question when we're trying to implement an operating system that focuses first and foremost on security is essentially that we must ensure the integrity of the reference monitor. If the reference monitor is there to ensure effectively the integrity of the access control decisions of the system, then that reference monitor itself must be free from corruption or influence from the principals on the system, right? So it must be implemented somewhere within the system in software, typically, although there are some systems that do it in the hardware, interestingly. You can look up enclaves or SGX to get some sense of that. But typically it has to be implemented somewhere in the system, and it's very natural for it to be implemented in the kernel, right? Dual mode protection makes it so that the kernel is isolated from the ill effects and the malicious effects of the principals executing above it in processes. So it's natural that we would use that dual mode protection to isolate the reference monitor from all of the principals in the system, right? But that does mean that we have to ensure the integrity of the entire kernel, right? If the reference monitor is in the kernel, then the entire kernel becomes an attack surface for the principals within the system. And if we must ensure the integrity of the reference monitor, that now means also that we must ensure the integrity of the entire kernel, which is to say that that it doesn't have bugs that the principals can in some way use to do privilege escalation or corrupt in some way the reference monitor. So this is hard, right? How can we implement some code that we know is correct, right? Especially when we don't just need the reference monitor, we need the surrounding kernel and its mechanisms as well, right? So how do we even think about the optimizations required for this? Well, we typically think about a trusted computing base or a trusted code base, a TCB, and that's effectively all of the code on the system that must be trusted to ensure the correctness of the reference monitor itself, right? So this certainly includes everything in the kernel, because if there's a bug in that, it could corrupt the reference monitor. The trusted computing base also includes hardware factors as well. So that is certainly part of the trusted computing base. But if we just focus on trusted code base, that definitely includes the kernel as well. So what we typically want to do is focus on economy of mechanism here, which again means that we want to make this reference monitor be implemented in as simple a way as possible, and that the surrounding kernel itself is also as simple, terse, and easy to validate that it's doing the correct thing as possible. And we've already talked about a class of systems that tries to effectively make most of their logic be based around effectively these goals. And these are microkernels. So with microkernels, we try to remove as much of the policy from the system as possible and maintain only the simple mechanism within the kernel, right? And we can really think about the reference monitor being co-located with that very simple mechanism and indeed being part of it. So now the microkernel, its job is to provide IPC between the different servers on the system, the different processes, the different principals on the system. But its job as a reference monitor is also to select who should be able to do which versions of IPC with which other principals within the system, other processes within the system. So generally, it makes a lot of sense to put microkernels with the secure operating systems, because microkernels' goals are often in line with making a reference monitor be as secure and trusted as possible, trustworthy as possible. Okay, so we've talked about a few things so far today. We've talked about security in general, which is really a cross-cutting design challenge. We need to decide not just what the resources and principles are in the system, but also how to ensure that the proper permissions are assigned for different principles to those resources, and then how to design the actual mechanisms in the system to ensure that only those designated operations can be performed, right? So we dove into the reference monitor, which encapsulates a lot of these trade-offs, and that's essentially answering the questions of how do we design it to be secure, how does it make its decisions, i.e. capability tables versus access control lists, Capability tables are often used in microkernels to provide this mixture of a microkernel and a reference monitor. And then what policies should be used to guide that structure, to guide the contents of all the capability tables within the system. So I hope this has been interesting. I have not gone into actually that many details about security. This is very much a 10,000 foot view of how to think about security. So please feel free to ask any questions. I'll try to answer them in the FAQ. Thank you very much. Have a good one. Talk to you soon.